Yes, I can. Yeah, it looks great.
Perfect.
Okay, maybe we should go ahead and start. So it's great pleasure to have Valentin Bosshard joining us from Zurich. Will be telling us about Lagrangian cobordism group of Weinstein manifolds.
Thanks a lot for having me here today, and also Happy New Year to everybody. So in this third talk, we are going to think about the computation of the Lagrangian cobordism group of Weinstein manifolds. So what is that? What is a Lagrangian cobordism? If you're in the setting of a symplectic manifold X, then Arnold already in the 80s defined Lagrangian cobordisms as a Lagrangian submanifold that lives in the product of the complex plane with our symplectic manifold, such that if you project this V to the complex plane, then it looks like this green submanifold. And it has a property that outside a compact region of the plane, it just looks like a product. So this means that, for example, here we have a ray in C times L1. So this would be gamma 1, and over each point here on this ray, we have a copy of L1 in our of this Lagrangian L1 in our symplectic manifold X. So this L0, L1, L2, L3 in this case, we call them the ends of this Lagrangian cobordism. So what can we do with this definition? We can classify Lagrangian submanifolds up to being Lagrangian cobordant. We are sometimes interested in just restricting our attention to a particular subset of all Lagrangians, for example, some topological properties like being compact or embedded versus immersed, or maybe some more symplectic properties like exact Lagrangian submanifolds, monotone symplectic manifolds, and also our Lagrangian submanifolds sometimes come with extra structure like an orientation and so on. We are free to choose whatever class we look at. Then our main study of object today that we want to compute is the so-called Lagrangian cobordism group. It's defined as the free abelian group generated by all Lagrangian submanifolds in our class, modulo the relation that we say the sum of Lagrangian submanifolds is 0 whenever there is a Lagrangian cobordism, also here star, so of the same class of Lagrangian submanifolds, but in the product, such that the ends are a 0 until Lm. So this is just a definition that we can do and try to compute this. Maybe just that you get a feeling of how this may look like. In this Lagrangian cobordism group, if L is an oriented Lagrangian submanifold, then if you reverse the orientation, this will produce a minus sign. So L bar is equal to minus L in the Lagrangian cobordism group. And for that, you just need identity cobordism. Maybe you have seen something similar like that. You need to be careful here a little bit about the sign of the sum to be 0. The signs are correct when you choose a grading on your cobordism V that induces a grading on each Lagrangian, and then you get the correct signs. But I don't care so much about that. But yeah, this is how you get this minus here. Then also in this Lagrangian cobordism group, if two Lagrangian submanifolds are Hamiltonianly isotopic, then they're equal in the Lagrangian cobordism group. This is called the Lagrangian suspension cobordism, which it goes also back a while, was already looked at. Then a third relation that is very important in this Lagrangian cobordism group is that if two Lagrangian submanifolds intersect transversely just in exactly one point, then you can do surgery to resolve this point. And what you get is again an embedded one. This was the condition that we just have an intersection at one point. So you get an embedded Lagrangian submanifold again. And the claim is that there is a Lagrangian cobordism with these three ends, the surgered one and two original Lagrangian submanifolds. And this will produce me that the relation that the sum of the original Lagrangians is equal to this surgered one. So maybe you should think about that we want to take the union of L0 and L1, and this equals the sum actually in the Lagrangian cobordism group. And just that we have an embedded one, again, we do surgery. Okay, so the main result is that it's just a computation. How do these Lagrangian cobordism groups look like in a very particular case, in the case of Weinstein manifolds? And in Weinstein manifolds, I will define that a little bit later again, but for now, let's just assume you know what this is. For Weinstein manifolds, we usually consider exact Lagrangian submanifolds that are conical at infinity. This just means that they are invariant under the Liouville flow at infinity, outside a compact set. And we also want them to come already with an orientation. Then the claim is that the Lagrangian cobordism group is simply cohomology of the Weinstein manifold. And if you prefer to work with homology instead, then you get relative homology. And such that you have something to be relative with. It's relative the boundary whenever you take, instead of the Weinstein manifold itself, just a Liouville domain or a Weinstein domain. What is this identification, this isomorphism? It takes a Lagrangian submanifold and it just sends it to its relative cohomology class. I mean, you can, to each Lagrangian submanifold, you can associate just the induced relative cohomology class, which will be in N. Let's see an example. If X is a cotangent bundle for a compact of a compact manifold, then by the theorem above, this tells me that we get cohomology of the cotangent bundle, which is cohomology of the manifold itself. And this is always generated by one object, but there's a difference if M is orientable or M not orientable. In both cases, it's generated by a fiber. And maybe just that you imagine why this torsion comes from in the non-orientable case, because if you have a fiber in the cotangent bundle of a non-orientable manifold, there is a loop in the manifold that is orientation reversing. So if you just transport your fiber along this loop, you can get back to the fiber again, but you end up with the opposite fiber. So this will tell you that L, or the fiber, is equal to minus the fiber in the Lagrangian cobordism group, because this moving the fiber is Hamiltonian isotopy. So this is also the equivalent result in the Lagrangian cobordism world to, maybe you know that Abu Zaid's result, that the fiber generates the wrapped Fukaya category. So this is the analogous result in the world of Lagrangian cobordisms. So there were already previous computations of these Lagrangian cobordism groups. I just mentioned some of those. Arnold already, when he defined them, computed one for the plane and also for T star S1. And he looked at basically all compact Lagrangian submanifolds, so immersed circles and also equipped with orientation. And what you get is you just associate to the Lagrangian, to the circle, you just associate its homology class. Then there's an area factor. I mean, circles can enclose some area if they're also in the plane. So this is this R. And then there's a Z, because the circle can have a rotation number. If you, for example, think of the figure 8 in the plane, this has rotation number 0, and just a circle has rotation number 1 or -1, and so on. So there were some more computations of surfaces, this time the compact surface, the 2 torus. Haug considered 2014 non-contractible circles, non-contractible simple circles. And this was already viewed towards a story where you can do Floer theory as well. So actually the computation is quite hard. It's not that a short paper. So already in dimension 2, things are not so easy. And there's also some mirror symmetry in this paper going on. So it's not at all trivial. And what we figured out is that you also get homology plus some area factor. The area factor is somehow, if you have fix one circle then and want to get to another one, you get some flux. This was generalized to higher genus surfaces by first tried by Perrier and then completely done by Rattel-Fournier in 2023. And you somehow again get homology plus some other topological property plus some area factor. Then also I tried to look at what happens for surfaces with boundary, so Liouville manifolds in dimension 2. And if you restrict to now, because we have a non-compact manifold, so maybe you want to allow not as just Arnold, you also want to allow non-compact Lagrangian submanifolds. So you want to allow some arcs that go from boundary to boundary, but you just consider exact Lagrangian submanifolds, so just exact circles. What you get, I mean, it should be compatible with the main result, is that in dimension 2 you just get cohomology or relative homology. Note maybe also that this exactness restricts our group quite a lot, so we don't have any R factor anymore. So this is just it's singular homology over Z. So because of exactness, we don't get that many different Lagrangian submanifolds. Okay, maybe you wonder the bigger picture, why I want to look at this computation. Actually, this Lagrangian cobordism group went into a bigger picture, and this is the following. This now works for any Liouville manifold, not just Weinstein manifold. That these are the two groups that we have already seen before, the Lagrangian cobordism group, that there is always a map to that associates simply its cohomology or the Poincare dual relative homology class of the Lagrangian submanifold. Then here we have symplectic homology, we have Hochschild homology, the open-closed map. Then here is the Grothendieck group of the wrapped Fukaya category of X. And this map here was studied a lot. So this map is interesting because why it's well defined, because by Biran and Cornea, they celebrated the result that Lagrangian cobordism induce cone decompositions in the wrapped Fukaya category. So some exact triangles in the wrapped Fukaya category are recovered by Lagrangian cobordisms. And this map here measures how much of exact triangles in the wrapped Fukaya category are recovered by Lagrangian cobordisms. So because both of these groups are generated by the Lagrangian submanifolds, and all relations, all cobordism relations induce relations in the Fukaya category. This map is always well defined and surjective. So you might wonder, is this map always an isomorphism? And the examples that we had until now, the ones for surfaces that I showed you before, this map was always an isomorphism. But it was not known if it's always an isomorphism in all cases, and the answer is it's not true, because I can now, using this theorem here, I can give now an explicit example. This is the following, that if X is a flexible Weinstein manifold, then the wrapped Fukaya category is 0, so the K group is also 0, so this group vanishes here. But on the other hand, the Lagrangian cobordism group, because it's equal, so this map is an isomorphism in case X is Weinstein. This was the first theorem. And cohomology is not 0 if X is not subcritical. So because this is an isomorphism, also the Lagrangian cobordism group is not 0. So this produces an example where this map is not always an isomorphism. Okay, maybe another quick application that maybe you know about Viterbo restriction in symplectic homology, Viterbo restriction for the Grothendieck group. You can do something similar for Lagrangian cobordism group using this theorem before, that if you're in the setting of a Liouville manifold and you have a Weinstein subdomain, so you have a subdomain that doesn't necessarily complete to X itself, but is really something different, then you can do the following, just using this map I that I said is well defined, going from the Lagrangian cobordism group to cohomology. Then to you go to cohomology of Y using just the map given by the inclusion of Y into X, just contravariant in the other direction in cohomology. And then these two groups are the same because Y is Weinstein. So actually you get the map from the Lagrangian cobordism group of X to the Lagrangian cobordism group of Y. And this is the analog, again, in the Lagrangian cobordism world of Viterbo restriction. Okay, this was it about the motivation. Now some more minutes about some arguments why this is true. Again, let's repeat what we need to show. We want to show, this is our main focus, that this map exists and it's an isomorphism if X is Weinstein. Well-definedness is actually quite quick. This map exists because we need to prove that if you have a Lagrangian cobordism, because this defines a relation in this group, we need to prove that it also gives me a relation in, let's say, in relative homology. And the argument is the following, that the Lagrangian cobordism, you can just look it as a relative n+1 cycle in X by just projecting V to the X part. And it's an n+1 cycle with boundary n chain, which is, if you check carefully, it's exactly the sum of the Lagrangian submanifolds as elements here. So yeah, you get that you get the relation that you want. So this already proves well-definedness. So to prove now that this map is an isomorphism if X is Weinstein, let me just repeat what Weinstein means. Weinstein means that X is a Liouville manifold such that the Liouville flow is gradient-like for a Morse function. So for example, the pair of pants with the height function, so the Liouville flow just points everywhere upwards. Some important subsets are the core, it's the deformation tract of X itself. And these are the points that don't escape to infinity under the Liouville flow. And this also coincides because X is Weinstein with the stable manifolds of the critical points, because the critical points of tangent functions are here, here, and here. The stable manifolds are exactly these red circles. So dually, there are the co-cores, and co-cores are simply the unstable manifolds of the critical points of highest dimension. You can prove that the index can never be higher than n, so the highest dimensional one are probably kind of interesting, and they are actually Lagrangian submanifolds, these co-cores, and which are isomorph, which are Lagrangian copies of Rn. So these are two important properties. So let's get back to what we want to prove. We want to prove that this map is surjective. So why is it surjective? So given an element, now let's think no more about relative homology, but about cohomology, but Morse cohomology. So we want to prove that there's a Lagrangian L that is mapped to the critical point, if you look at Morse homology, Morse cohomology. So, and this is simply that for a critical point of index n, the co-core is a Lagrangian submanifold, and if you check, the co-core under this map is associated with X itself. So you get surjectivity almost for free in case X is Weinstein. But this already relies, surjectivity relies on that X is Weinstein. It's not true in general if X is just Liouville. To prove injectivity, we rely on a theorem, on a construction given by Andrew Hanlon and Jeff Hicks in 2022. they produced a very nice Lagrangian cobordism that is the following. That I have also a picture here, so you can already better imagine what's going on. The core of X is here again drawn in red. So for every core, for every smooth part of the core is always a singular Lagrangian submanifold. For every smooth part, there's a co-core. So for example, here we have this one, and the third one here. And the claim is that if you have a Lagrangian submanifold that intersects the core transversely, so the Lagrangian submanifold here, L is in green. So we have 3 intersection points, one here, and one here. Then the claim is that actually there's a cobordism between L itself and the co-core at this point, and at this intersection point. So the Lagrangian cobordism group, we have here this co-core, because you just can transport it here over here by a Lagrangian isotopy. Then we actually get minus the same co-core again, because now if you look at L, it goes in the other direction than the co-core, so we get minus this Lagrangian co-core. And then here we have a third intersection, so this so just plus this core here, co-core here, because it goes in the same direction. So the two first cancel. So actually in the Lagrangian cobordism group, you already see somehow you can make this Lagrangian disjoint from this part of the skeleton. So just this part here is relevant. Okay, so what does this prove? It proves that every Lagrangian submanifold, if you just deform it a little bit, you can make it transverse to the core. And then you can just decompose it as co-cores using a Lagrangian cobordism. So here you see the Lagrangian was general in the beginning, and then it's just a sum of co-cores. So actually, Lagrangian cobordism group is generated by co-cores. Yeah, maybe I have just some minutes left. So what we need to prove in the very end is that what we know now is the first group is generated by co-cores modulo relations by Lagrangian cobordisms. The second group is generated by critical points modulo the relations coming from Morse cohomology. And Morse cohomology relations are the following: that for every critical point of index n-1, you look at all Morse trajectories that you have to critical points of index n, and then you just say the sum is 0. This is what Morse cohomology is. So what is left to prove is that these relations here, because we already know that from here to here, the map exists, so Lagrangian cobordisms induce relations also in cohomology, so we need to prove the other way around, that any relation of this form is induced by Lagrangian cobordism. So this is the following: if we have, if we fix a critical point of index n-1, and we have Morse trajectories from y to xj for some xj's, then the sum of the co-cores is 0. And I would like to finish by this picture. This picture should give already the complete proof. This argument is following Lazarev, so he proved something similar, so I could borrow some steps from there. And it works like the following, that as said before, we need to look at this critical point of index n-1. So locally, this n-1 handle that corresponds to this critical point y looks like that. This is a handle, a Weinstein handle of index n-1, because this is subcritical, and this one, yeah, has index n-1. So the picture here is just the B2 part. We just project to this to the plane, or I mean, you see the ball here, and from there we have these Morse trajectories going away to critical points of index n. So for example, a handle attachment would be that it goes to the critical point xj, and in my case, there's two Morse trajectories going to this critical point. So in my case, this xj is actually equal to xk. Okay, this is the local picture. What does this help us? The co-core is here to the critical point. So this dotted part, you should think about this is where it goes to infinity. So the co-core is this copy of Rn that is dual to the core. So let's introduce some other Lagrangian submanifolds which are dual to these Morse trajectories. So in B2, it's just the arcs that connect the different parts of this Weinstein manifolds. So if you look closely, you can see that this Lagrangian submanifold, you can just move it along this part to be actually the co-core. So if you take the product of this gamma j with a Lagrangian submanifold, you need to have a Lagrangian submanifold. So you have an arc here plus bn minus 1, the zero section. You get a Lagrangian submanifold that if you transport this all the way over here, that is actually this equivalent to the co-core by a Lagrangian isotopy. So this one is a co-core or equivalent to a co-core. This one, this one, this one, and this one. And we're almost there, because if I go first here with this Lagrangian submanifold, then here, then here, and then here, and then here, then I get back and do surgery. So because I can do surgery from here to here, such that I get then an arc that goes directly from here to here. If I do also surgery here, I get an arc that goes directly from here to here. If I do surgery of this part with this part, I get an arc that goes directly here, and so on, such that I end up with an arc that just lies here. And this doesn't intersect the core, because the core is the red part. So we get something that is Lagrangian isotopic to Lagrangian cobordant to 0, because before I said it just is relevant where you intersect the core. This was a statement by Jeff Hicks and Andrew Hanlon. So not just the sum of these gamma j's is 0, but also the sum of the co-cores is 0, because the co-cores are the same as this bn minus 1 times gamma j's. Okay, this is all what I wanted to talk about. If there are any questions, I'm open, and also Happy New Year. Thanks a lot for listening.
Thank you. Okay, let's thank Valentin also.